Good day, everyone. Aside from the position vector to describe the motion of the particle, the velocity vector is another way to describe the motion of any particle. So in this video, let us understand on the average velocity and instantaneous velocity vector. Now in previous video for the position vector, we understand that any particle can be described in space provided that we have the frame of reference. So in this case, we have a three-dimensional frame of reference. Then it follows that the position of the particle can be described as position 1. So let us say r sub 1. Now the position has three components. Remember in previous video we learned that there are components of the position. It can be x, y, and z because this is in three-dimensional reference line. So the position happens only because of the time. Now for every time there must be a position. Why? Because position is a time dependent, meaning there's no position without time. And we can say it that the particle is located at the initial position. Now when the particle travels to another point, then we have another position, and we can call that as, let us say, R2. And R2 happens because of the position or the time interval or the time 2. Meaning at time 2, we have position 2. And if we say final position, then it follows that the particle starts from initial point, then it ends up to the final position. Now, at any time of travel from T1 to T2, we can represent that as, let us say, r hat. R hat, which is a function of time. So we call this as the position vector at any time between T1 and T2. So it is the variable is time, meaning at any time when you substitute t to the position vector, then we can always compute the position of that particle. So if the time t1 be substituted to the position vector, then we can find the r2. Similarly, if we substitute the time t2 to the position vector at any time, then we can compute for r2. So within the time interval or time given, we can always find the position vector. Okay, now the line that connects from initial towards the final, take note, is the change in position, as we learned in our previous video. So the change in position, take note, is also called as the displacement of the particle. Okay, now the delta r, or the change in position or the displacement, mathematically can be computed as the final position always minus initial. Take note, always final minus initial. Now since the time is dependent, the position is dependent to the time, then we have the so-called time interval between the 2 points. So the time interval represented by delta t, and the delta t can be computed by subtracting the final time minus initial. So if you subtract the final minus initial time, we call that as the time interval. Now meaning the time is another way to describe the particle in motion. Okay, and take note that the time is a scalar quantity, so we don't have the direction. Unlike for the change in position or velocity, it has the magnitude and direction. Now, if we divide the change in position by the time interval, this is called as the average velocity, or in symbol we have v vector of average. Okay, so again, if we divide the change in position per time interval, that is the average velocity. Okay, now let's have the problem. Suppose the particle travels from point 1 at time 1 second, and it end up to another position, which is the final position, at time t2, let us say 3 seconds. And the position vector, meaning the position at any time, let us say, given as 5t I hat plus 3t squared j hat minus 2k, and the units is in meter. So suppose this is the description with travel. It has a position vector at any time in that equation 5t hat plus 3t squared g hat minus 2k hat. Okay, so meaning with that we can always find the position because we are given 1 second for the initial, and we have 3 seconds for the final position of the particle. So meaning we can always provide the position vector initial and the position vector final. Why? Because we have the position at any time. So by substituting the time to the position vector, then we can compute the R1. So substituting the 1 second to the equation, meaning replace t with 1 second, then calculate, then we come up with a position initial or initial position as 5 I hat plus 3 g hat minus 2k. This is the first position of the particle. And for the final position of the particle, again using the position at any time, replace t with 3 seconds. So you have to substitute t 3 seconds for the final time. Then simplify, then we come up with 15 I hat plus 27 g hat minus 2 k hat. And these are the initial and final positions. We are able to compute, we are able to compute the initial position because we have the position at any time. So these are the result. R1 is 5 I hat plus 3 g hat minus 2 k hat, while R2, the position 2, is 15 I hat plus 27 g hat minus 2 k hat. These are the two positions. Now, from there, take note that we can compute the displacement. Take note that we are about to solve for the average velocity vector. So how? We need to compute for the change in position. Now we can compute the change in position for the reason that the initial position and final positions are provided or were provided. So then substitute the position 2 minus position 1. Okay, then you have to remove the grouping symbol. Take note again, for the vectors algebra, we can combine the like terms are terms that contains the same unit vector, and the unit vector are I hat, j hat, and k hat. So when you remove the grouping symbol, combine the like terms, it results by 10 I hat plus 24 j hat. The k component was eliminated because when you look at the equation, the 2k, negative 2k, by subtracting is actually 0. Okay, so we have now the position, the change in position, which is 10 I hat plus 24 j hat. Now, we need also to compute the interval. Why? Because as I've said, we are computing the average velocity. So, the time interval can be computed by subtracting the final time minus T1 minus the initial. Meaning, it should be T2 minus T1, or it is 3 minus 1, and the answer is 2 seconds. This is the time interval, 2 seconds. Now, since we have already the change in position or the displacement of the particle from initial towards the final, and we have the time interval of 2 seconds, we can now compute the average velocity by dividing the change in position or the displacement by the time interval. So replace the value of the change in position 10 I hat plus 24 j hat divided by 2. Then take note that you can simplify this by sharing the denominator of 2, then divide the number by 2, and we come up with 5 I hat plus 12 j hat. This is the answer to the problem. We call this as the average velocity vector. And we notice that the average velocity vector is actually lying on the xy plane. The reason is because the components present on the answer contains I and j hat, which means that there is no velocity with respect to the z-axis. because of the absence of the k hat. So this is the average velocity vector. Now suppose you are asked, what is the magnitude of this? Remember that average velocity is a vector. So meaning, we can provide the magnitude of that velocity using our previous topic on the in vectors analysis. So calculating the magnitude of the average velocity, take note that we can use the square root, no? The square of the components, no? The square of the components, the square root of the sum of the squares of the components is actually the magnitude of the vector. So we have the square root of 5 square plus 12 square, and the answer is 13 meters per second. Meters per second is because that the position is in meter and the time is in second. Okay, so the magnitude of the velocity is 13 meter per second, and the velocity vector is 5 I hat plus 12 j hat. Now, if you wish to compute the angle of this velocity with respect to x, then you can use the tangent, no? Inverse tangent, then we have the 12 divide 5, no? Meaning the y component divide the x component, then you can compute for the angle. Okay, so these are the solutions to the problem in finding the average velocity. So generally, again, when we see average velocity vector, it is what? Change in velocity or change in position per time interval. So it requires what? Initial position, the final position, the initial time, and the final time. If you have that 4 quantities, we can always provide the position or the average velocity vector. That's it. Now, next question. How do we compute the instantaneous velocity? Okay, now what is instantaneous velocity? From the word instantaneous, no, it is at a certain instant, meaning we are to calculate or to find the velocity of that particle at that specific point. Now we look at the travel is from point 1 to point 2. There are many positions that can be obtained. Now, the position of the particle at any point of travel, there must be an instantaneous velocity. So in that case, at T1 there is an instantaneous velocity. At T2 is another instantaneous velocity. At any time of travel, there is always an instantaneous velocity. So how to compute the instantaneous velocity? Okay, now how we do it? Now take note, in our average velocity, we compute the average velocity by dividing what? The change in position per time interval. Okay, now for instantaneous velocity, we still need divide, diba? We still need divide the position, because velocity means it is the change in position per time interval. Now if we reduce the change in position, if we make the change in position delta r as a very, very small, so meaning when we consider only a very, very small displacement within the travel, okay, we reduce, then the delta r becomes dr. So in mathematics, when we say dr, it is an infinitesimal value of r, meaning it can be read as the infinitesimal value of the position. So we call that as a change in position, but in a very, very small. So we replace the delta r with d. Take note of that, so meaning it will be a very, very small. Now if we have a very, very small displacement, then we have a very, very small time interval also, and we call that as dt. In mathematics, dr means the derivative of r, and dt is the derivative of t. So the word derivative means it's a very, very small. So with that, we can divide the dr over dt. If you divide the dr over dt, this is called as the instantaneous velocity, or the velocity at a certain instant. Take note, we are not talking with an interval between T1 and T2. This is not between T1 and T2. It is an infinitesimal displacement. So therefore, we can say that the instantaneous velocity is the derivative of r with respect to time interval, meaning dr over dt. In mathematics and calculus, it reads as the derivative of r with respect to t. Or we can rewrite this as the d dt of r, meaning the d dt is the derivative operator, and the operator will operate to the position r vector. So the derivative of position with respect to r is d dt of r. So you have to recall your calculus. Okay? So then, sige. Suppose you are given the problem, suppose given the position vector, because the instantaneous velocity can be calculated if we have the position vector, meaning it requires position in order to produce instantaneous velocity. So suppose given, now take note, if you notice, we have the same equation in the average velocity, or the same position vector, the 5t I hat plus 3t squared j hat minus 2k hat. But this time, our problem is what is the velocity of the particle in 1.5 second of travel. Take note that the particle previously, it start from 1 second, then it end up to a time of 3 seconds. Now, the question now is, what is the velocity when the particle is in the time of 1.5 seconds? So how you answer this problem? And the given is the position vector, meaning the position as a function of time. Now, to do it, take note that the instantaneous velocity is the derivative of the position, and we have the position. So all you need to do is to take the derivative of r with respect to the time. And take note that the time is what? The time is the independent variable of that equation, while r is the dependent variable. Okay, so again, in order to calculate the velocity of the particle in 1.5 seconds of travel, then we are calculating what? The instantaneous velocity, because the requirement is in the second, or in the time of 1 second. And there's a follow-up question, find also the magnitude. Now, the magnitude can be easily calculated if we have the velocity vector. Remember that, okay? So, therefore, your solution will start from, in order to calculate the instantaneous velocity, or say it as v vector as a function of time, or vt, then this should be what? The derivative of the position with respect to r. The operator is d dt. So, using our calculus, okay, substituting the position, then apply the rules of differentiation. So, you need to recall the rules of differentiation. Now, particularly, or in this problem, we need the sum rule. So, meaning you have to review, no, the rules of differentiation. So, first is to apply the sum rule. So, meaning you can break that into individual terms. So, meaning what is the derivative of 5t I hat, then what is the derivative of t 3t squared, then minus the derivative of 2k. Now remember that the variable is t, okay, with respect to t. So after that, you have to apply the rule of what? Another rule is power rule. Okay, so when you apply the power rule in each term, the result becomes 5 I hat plus 6t hat, because the first term, the 5t I, the t is in the first degree variable. When you apply the power rule, it will becomes t, the exponent becomes 0. So the t raised to 0 is 1. So we leave only with 5 I hat. While the second term, the 3t squared, using the power rule, now after applying the power rule, multiply it by 3. Or you can say it 3 times 2, then t squared minus 1 by the using the power rule. So you can, the second degree will reduce to the first degree. That's why the answer is 6t j hat. Then notice that the answer is only 2 terms. Why? Because the 2k is a constant. It can be treated as constant because there's no variable. And remember, in our theorem of differentiation, the derivative of a constant is always 0. So we have only 5I hat plus 60j hat. This is our velocity, instantaneous velocity, or we call this as a velocity vector at a certain point. This is different in the average velocity, no? Because you are differentiating. You are not obtaining the change in position between two interval divide by the time interval. This time we differentiate it with respect to time. Okay? So now, since the question is velocity at a certain time, which is 1.5, now the result 5I hat plus 60 hat is the instantaneous velocity at any time. At any time, meaning at any time of travel, you can substitute the value of time. Okay, then simplify, then it will provide the answer. So when you if we calculate the instantaneous velocity of the particle at 1.5 seconds, then we have to replace t with 1.5 seconds, then simplify, then the result is 5I hat plus 9j hat. Okay, then what next? Okay, then this is now the velocity vector at the time 1.5 seconds. But there is a follow-up question. Find the magnitude of that velocity. So all you need to do is, again, when we say magnitude and we have that vector, think of the square root. Okay, the square root of the components, no, the square of the components, the sum, the square of the component, and take square root. The answer is the magnitude of that of the velocity. Okay, so then simplify further. We will come up with 10.3 meter per second. This is the magnitude of the instantaneous velocity, while the 5I hat plus 60 hat tj hat is the instantaneous velocity at any time. So if there were follow-up question, what is the instantaneous velocity at let us say 2.5 seconds, then substitute it to the instantaneous velocity 5I hat plus 60 hat. So replace the t with 2.5. That's it, no? So meaning you can use it because that is the result after differentiating. Now differentiation provides the velocity. Okay, so in review, in order to find the average velocity, you need to obtain the initial position and final position, and the initial time and the final time. Then with that, you can take the change in position per time interval, then that's the average velocity. While in instantaneous velocity, or the velocity at a certain instant, all you need to do is to use again the position vector, but this time you need to differentiate. So the idea of calculus is very, very much important if we are talking about instantaneous velocity. Okay? Now, for your practice, this is a good problem. The same position vector in meters, but the question is, at what time will the particle be in at rest position? Now take note that previously the result that the velocity at 1.5 seconds of travel, it has a 13.9, I think, meter per second. So meaning it is in motion. Now how can we say that the particle is at rest when the velocity is 0? So the question now is, at what time will the particle be at rest or in rest position? So all you need to do, okay, the same process, you need to differentiate this one with respect to time. Then after that, the result will be equated to 0, because when you equate the derivative of the position with respect to time equated to 0, you are actually equating the velocity which is at rest, because 0, the velocity is at rest. Then after that, compute for the time, use your algebra. So in that case, you will determine in what time that the particle is at rest. Now take note that when you look at the equation, the time 0 is not at rest. Have you seen it? Diba? If you substitute time in the position b equal to 0, the result is negative 2k, which means that the particle has what? Has a position. Diba? Has a position, meaning it has, if there is a position, there is time, then it follows that, what's that? Must be a velocity on that. Okay? When you look at also for the result after differentiating, when you equate to 0, the time, okay, when you equate time to 0, there is again a velocity. So, which travel that the velocity is at rest, meaning how much time in order the particle to be at rest. Okay, so that's all for today. Thank you for listening. So the next topic is talking about acceleration, Victor.